What I'd like to do today is to take us from those 5 basic graphs and see how really every equation that we encounter actually is rooted in these graphs, and then how they actually are in the form of a translation or some kind of a transformation to that graph, whether it's flipping it or shifting it or making it bigger by multiplying it, dilating it, or whatever. And so before I get too far into this, I want to just quickly remind you of those 5 basic graphs. Our 5 basic graphs starts with, we had the line y equals x, a basic line that runs through 0, 0, and a positive 1 slope. Easy enough. The second graph that I would like you to remember, of course, is the parabola, y equals x squared. And that, of course, all of our parabolas are rooted in that very graph. We have our basic log graphs or natural log graph, and I'll just leave it as logs, which would be, of course, the one that starts very close to the y-axis and crosses at 1 on the x. Our exponentials, any of our e to the x, 2 to the x, or any number to the x, follows the same pattern of those exponentials, which cross again at 1. And then lastly, we have those trig graphs that we have become so fondly aware of. And so we have those 2 quick little trig graphs. Good. So now as I look at these examples, I want you to be thinking about which one is the root graph that we're working with. And so as you look at this particular equation, y minus 4 equals x squared, which is the root graph? My hope is that you are thinking, oh, that's the same as y equals x squared. And so you would be right. That is the y equals x squared graph. But something's going on with that. And I want to take a couple extra minutes. Now, we won't for every one of these, but I want to take a couple of minutes to look at what is this graph exactly and examine what that negative 4 actually is. Now, we could look at our properties and we could actually solve this equation, and maybe we even do that. We look at that equation like we used to and solve for y and then just see what happens to the graph. Or you could look at this chart as another means to do that. This, of course, would tell me that the y-intercept was at 4. And the x-intercept, you would quickly find that it's imaginary, so therefore there's no x-intercepts. And you do the turning point, which would be x equals negative b over 2a, and of course you find that b is 0, and so the turning point is 0, 4. So all I have then is the point 0, 4. It's our turning point. It opens upward, and so that's what that graph is. Now I want you to take a moment to look at that root graph and say to yourself, is there a way that I could have linked from that basic graph to this y minus 4 equals x squared and see it as a transformation instead? My hope is that minus 4 stands out to you and that could have given us some clue as to what happens with the parabola. Well, let's look at another one. Now let's look at y equals and then have x minus 2 squared. Looking at it in the old way, we would have multiplied that out. And again, you'd find the y-intercept to be 4. The x-intercept would have been when you factored, of course, with the x minus 2's, finding that you get x equals 2 times. Your turning point would have also been at 2, and you plug that in, and of course finding out that y is 0. So you have the point 2, 0, and you know it crosses on the y at 4. Is there a way, and of course begs the rhetorical yes, but that we could have linked to y equals x squared, and what happened to that graph? What in this tells me that all it did was shift to the right 2 units? Is there a way to do that? My hope is that when you see that minus 2 there, that you recognize that, oh, that's with the x's. And of course, the x's determine our right to left movement. And that minus 2, and yes, it is in the opposite. It's not going to the left 2, it's going to the right 2. That is enough clarification for you to see there is a relationship between that equation, obviously, and the graph. with that in mind, now let's look at this question here. Y minus 3 equals the natural log of x plus 1. Well, first of all, we need to recognize the root graph of this. And my hope is that you're thinking, in your head, you're thinking, okay, wait a minute, this is the natural log graph. But these numbers mean something. And so what is, in fact, that relationship? What does that minus 3 tell me is going to happen? My hope is that you can see that that means I'm going to shift up 3 units. It goes opposite of that sign. And what do you think is going to happen to the x's? Again, that's the right to left motion, and so that would mean that I'm going to the left 1. So what I'm basically going to do is I'm going to take this graph here, and I am going to shift it, and I'm just going to unlock it here. I'm going to shift. I'm going to go to the left 1, and I'm going to go up 1, 2, 3. And so that natural log graph now looks like that. Isn't that amazing? So it starts with that lovely natural log graph, and it would go to the left 1 and up 2, 3. And so the way I would focus this, or if I was doing this on my own, is start with the 1 point you know, in this case 1, 0, and how does that affect that point? That point now becomes the point 0, 3. And so I would mark that. That's what I'm looking for in the grading of this. Okay, let's try this last one. Y plus 1 equals, and then you have x minus 5 squared. Similar to the ones that we did in the beginning of class, my hope is that you recognize this as being a y equals x squared graph. And so you're thinking, okay, I've got a parabola centered at 0, 0. And so what's going to happen to this graph is it's going to shift. And so I'm going to shift it. How? I'm going to shift it to the right 5, right? To the right 5. And then what am I going to do to the y value? I'm going to go down 1. And so this becomes 5, negative 1. Now, do you recognize something about this? The turning point has become quite obvious. In fact, this is what they call the vertex setup, where you can see the vertex or the turning point as being 5, negative 1 right from that equation, and as quick as it can be. Now, if you had Mr. McCarthy, you probably learned the format that once you found that vertex or the turning point, then you know the pattern as going over 1 and up 1, over 1 and up 1 in both directions. And so this would be at a turning point of 5, negative 1, but with the root of 6 and 4 pretty quickly. Great, and I hope that explains to you, or at least shows you something. Tomorrow in class, when we start practicing these, my hope is that you can see these equations not just as the root graphs, but also as a transformation.